Mathlouthi. He is president of the association, French Association, on the part of STAI. Chemistry, published 8 books, and still had 150 papers. He is professor at the Leeds University, consultant and chairman of the association. His presentation is sugar crystallization and drying, basics and critical aspects.
So it's lunchtime. I try to hurry up. First, I would like to thank this second conference of the SI and to extend my thanks to Dr. G.S.C. Rao and my other Indian friends I have known with Dr. Rao. So my presentation deals with crystallization and drying, and both the aspects, the basic and the practical. We'll deal with the basics of nucleation and seeding, crystal growth, drying, cooling, water activity and storage, and then we'll see some practical aspects. You know, the aim of industrial sugar crystallization is to obtain good quality sugar crystals, good grain size distribution, color, fine, etc., and to achieve a high crystallization yield together with an optimization of energy consumption. How to achieve these objectives? The nucleation and seeding is the first step. It is the most important step, as we will see. Then the growth of crystals should be based on some sound criteria. The simplest and sound criteria are pressure, temperature, boiling point, elevation. I will recall that the growth proceeds in 2 steps and see the importance of each step, and then the progressive tightening, etc. This is an analysis, a routine analysis of good crystals. You see that water should be measured by Carl-Fisher titration, because what you measure generally is whale loss from oven 3 hours, etc. The Carl-Fisher titration gives you the real water content, and the surface water should be a little bit less than 1/3 of the total moisture. Grain size is very important, especially the presence of fines and the distribution. Now, I would recall my late Professor Marcel Lancin. He uses to say, theory is the easiest, most straightforward, and most efficient way to solve practical problems. But we will not make it the sophisticated theory with equation. We just will stay and see what is happening inside this solution of sugar. First, nucleation and seeding. In dilute solution, sucrose molecules don't see each other. As concentration is increased, they come together to form clusters. When a cluster reaches a certain critical radius, then we are ready to grow. In nucleation, the kinetics of nucleation, the frequency of nucleation is contains two terms, an anthropic term and an enthalpic term. This is the most important term as it is creating order, making solid out of liquid state. The nucleation, the seeding, because spontaneous nucleation is just an accident, but seeding should be made between this limit of the metastable zone and the saturation. A seed particle introduced here can grow easily without any false grain. But very often it happens that the concentration is too high and we have some false grain. The effect of non-sugar on the saturation is such that it can be either, depending on the type of non-sugar, create a salting out, decrease the solubility, or a salting in, increasing the solubility. In case of salting out, you introduce your seed and think that it is in the right zone, but because of the effect of non-sugar, it is in the labile zone, and then it creates these false grain. And on the contrary, if it is a salting in effect, your seed dissolves instead of growing. So the nucleation and seeding is just mastering the concentration at which we introduce the seed. The growth of crystals. When seeds or nuclei are formed and ready to grow, the excess of supersaturation in the model liquor is integrated into the crystal. And the faces of the crystals, there are many as you can see, have different growth rates. The growth proceeds in two steps. First, the fusion of sugar molecules or sugar clusters from the bulk of the solution to the diffusion layer. And then the second step is the integration of the sugar molecules in the crystal. The second step is the most critical. And Andrew Van Hoek uses to describe crystal growth as a hurdle race. The hurdles are made of activation barrier energies, alignment of molecules, hydration, water disassociation, etc. You have diffusion, surface diffusion, volume diffusion, and this step of integration of molecules inside the crystal is in fact very complicated if you want to study it at the molecular level. So the growth of crystals should be synchronized with the evaporation in the pan. This allows maintaining of constant supersaturation. The sugar coming with the syrup should be integrated in the crystal with constant supersaturation. The first step in growth is to assure a surface formation, and then you can feed and have a growth, a more rapid growth, because you can increase the steam flow, etc., to make the increase of growth. You can see, and also you have to adapt to the purity of the slide. The basic of sugar drying is that you can at any time establish a mass balance and a heat balance, very easily knowing the moisture inlet and outlet of the product and the air characteristics. Also for the heat balance, it's also easy to establish it using the steam tables, etc. Now, if we go a little bit through the basics of drying, we should remember that humidity is exchanged with air, and there could be dehydration or absorption of the humidity in the film of syrup surrounding the crystal, and also in the meantime there is always an exchange of sugar crystallization or dissolution. Here also, if you want to know the peregrination of water molecules going from the humid crystal to the drying air, you see that there are different interfaces. Crystal film interface, and this is the syrup of film, the film of syrup where water has to be disassociated from sugar and coming as a monomer to be taken by air. But sometimes there is a layer of amorphous sugar, and this layer of amorphous sugar delays tremendously the drying and also creates problems for tasting. So what differentiates the sugar drying from the water evaporation? Water vapor pressure of the film of syrup is different from water itself. Of course, there is a resistance to transfer in sugar syrup, which is absent from pure water. Crystallization of sugar in the syrup doesn't exist in water, and the possibility of forming these amorphous layers. The consequences of this amorphous sugar crust is, which is due to rapid evaporation from the outer layers and an insufficient rate of water diffusion to the inner layers. The consequences are high supersaturation of syrup at the interface, formation of an amorphous sugar crust at the interface, and water is trapped within the film of syrup, and this is causes a dramatic decline of the rate of drying. Now, a few words about water activity and storage stability. Sugar is not as hygroscopic as one can imagine. You can go until 0.8, which means 83% of relative humidity, without absorbing more than 0.01% of water. And when you reach this, you reach the critical water activity, and absorption of water becomes exponential. This proceeds through steps. First, absorption of water, then dissolution at the surface, and if you increase your relative humidity, you can even reach the dissolution of the crystal. How to determine the critical water activity at which we have these caking problems? You have to establish the sorption curve and take these tangents to determine the water activity or relative humidity at which the caking starts. Now, the practical aspects. The optimizing of seeding. Theoretically, the number of particles you put in the seed slurry are the same number as what you have at the end of crystallization. Supersaturation should be maintained around 1.15, 1.2, not above. And also you have optimize the steering high enough to prevent melting and low enough to avoid fine crystal formation. We'll see also the magma seeding, which needs some adjustment in temperature and crystal size. The quality of seeding crystal should be obtained by grinding the crystal. So it is better to have it doesn't work. This no. It is just a small video to show that broken crystals start by repairing this broken crystal, which is a trigger effect for growth. And they grow much better than crystals which are well formed but having defects. The choice of the dispersant. Ethanol is abandoned because it's almost the same temperature as the crystallization, 78 degrees. Then it was replaced by isopropanol, and isopropanol itself is not as good as it should be because there is some settling of the seed particles. Now, polyethylene glycol 300 is used, and we see that the dispersion in polyethylene glycol is better than in isopropyl, where there are some swarms of particles. In magma seeding, generally it is made by cooling crystallization, and the seed magma, the magma is heated prior to injecting in the different strikes. The temperature should be maintained, the difference of temperature between the heater, the cooler, and the syrup should be maintained constant to have this crystallization, cooling crystallization, optimized at a constant supersaturation. So supersaturation should be controlled by heating at the end of the cooling cycle from 30 to 34 degrees, and to lower supersaturation in the receiver. And the seed magma preparation ends to obtain a good CV around 32, which is the starting point to obtain a good CV at the end of the crystallization. The practical aspect of crystal growth, that a slow growth in the beginning to obtain surface and build the crystals, and you can build the crystals with fast growth, and the brixing is even a faster growth. But during the brixing and during this slow growth, it is advised to add water. Why to add water? Because the circulation of the mass heat inside the pan is made by evaporation, much more efficient than by the mechanical stir. Here you see a cycle of a pan, increase of supersaturation by evaporation, stabilization, followed by the graining, and then you have almost constant supersaturation, which decreases because you have to exhaust the mass heat. So the optimized condition for crystal, for pan boiler running, need that mass heat circulation mainly obtained by evaporation, in a lesser extent by mechanical agitation, the need of adding water to assure evaporation, syrup properties to monitor are flow rate and concentration, and supersaturation and the condition in the pan are dependent of many factors: the geometry of the calendar, the shape and height of the pen bottom, etc., etc. All these details, practical details, interfere. And the best way to control is to go to Charles' table of saturation and calculate your supersaturation to be in the 1.1, 1.15, no more supersaturation. And also you can use the literature for boiling point elevation. Now, there are always some impurities, and impurities sometimes change the shape of the crystal, and also there are inclusion in certain phases of the crystal. For example, having some dextran, you have these elongated shapes. Having some invert in the syrup, you have this type of shape, and the Kestos also gives these triangular crystals. Now some practical aspects of drying. This is what we shouldn't want to see in the factories. And how it comes by high temperature fast drying. Most of the factories have enough energy to put in the dryer. The tendency is to heat air and to dry at no. Only 60-65 degrees C is enough. Why 60 degrees? Because 60 degrees is the glass transition temperature of sugar. What does it mean? It means that these tiny particles or the amorphous layer become sticky at 60 degrees. So when you are above 60 degrees, you remove water without having this sticky phenomenon. So if you increase temperature, you increase the thickness of the layer of amorphous sugar. So better to stay no more than 65 degrees. Optimizing of sugar cooling. Cooling should be progressive. Avoid the shock of temperature. Final temperature after cooling should be above 5 degrees above ambient, no more. And air velocity should be sufficient to assure fluidization, because most of the time it is fluidized bed. Here you see if you are have a very high speed of air, you have entrainment, and if you have a low speed, it is not enough to make fluidization. Now the handling, screening, and conditioning also can cause these type of defects. They induce fractures, abrasion, and the particle breakage. Water content and water activity. Water content is better measured by Carl Fisher because it is a chemical reaction which measures water. It doesn't matter, it is, you have here description of the method to have total water, and if you saturate your medium with sugar, you can measure surface water. Very simple tool to measure sorption isotope. Just a tight jar and saturated solution of salt to have relative humidity fixed here, and then you put your sample. You can also control the flowability of your crystal with a very simple tool like this. You incline it and have the angle at which sugar flows. Sugar have been previously stabilized with different relative humidity, and then you see that the flowability angle is the lower the flowability angle is the lower, the higher the size of the crystal and the higher the water activity. So it is a way to measure the stability of the crystals. Now, to prevent sugar caking, sugar moisture should correspond to the equilibrium relative humidity. The composition of conditioned sugar should correspond to homogeneous production. People tend to mix A, B, and R1, R2, etc. for delivering to the commerce, but it is okay. So, to conclude, sugar stability depends on the quality of crystals. The quality of crystals depends on the supersaturation at which you introduce your slurry and you proceed to growth. The condition of pen boiler are supersaturation concentrated and controlled by temperature and pressure boiling point. The stability of sugar drying at 65-70 degrees is more than enough. Minimize the formation of amorphous and adapt sugar cooling to the ambient conditions. Water content and water activity, we have seen how to measure them, and they are very, very useful to predict the stability of sugar. And now, thank you for your attention.